Okay, great. Next up we have Matt Wetstein talking about A.N.N.I.E.
Good afternoon, everyone. I'm Matt Wetstein, and I'll be speaking on behalf of the A.N.N.I.E collaboration. A.N.N.I.E stands for the A.N.N.I.E stands for the Accelerator Neutrino Neutron Interaction Experiment. We are two things. One is we're a physics measurement aimed at better understanding neutrino nucleus interactions, something that Pedro did an excellent job of motivating the importance of. We're also an R&D effort focused on developing and demonstrating new neutrino detection techniques and technologies. In order to accomplish these goals, we've assembled a collaboration, an international collaboration consisting of 11 institutions, 3 nations, and we're a very young collaboration. We wouldn't be able to have accomplished nearly any of what we've done if it wasn't for the hard work of our 8 postdocs, 8 graduate students, and 20+ undergraduate researchers. This is a very exciting talk for me because we are just 2 weeks away from completing our construction, with commissioning scheduled to begin fall of 2019. The A.N.N.I.E physics program is what I like to call neutrino nuclear billiards. Just like in billiards, except with the cue ball being our leptonic system, if you have a 2-body scatter, it's very easy from the outgoing momentum of the cue ball to understand what the initial energy and momentum of the cue ball was. And similarly, in our case where we've got a neutrino coming in and a muon coming out, you can use the outgoing muon momentum to do a pretty good job of reconstruction in the 2-body case, but in much more complicated multi-body scatters and collisions and inelastic processes, the outgoing lepton is not enough to give you a complete picture, and you really need to understand more detail of the nuclear final states. Neutrons in particular are a major component of the nuclear recoil system, and they're also a source of missing energy in neutrino detectors. Even in the case of calorimetric energy reconstruction, given difficulties with reconstruction and efficiency in detecting neutrons, they still pose a problem. A.N.N.I.E measures the multiplicity of final state neutrons as a function of outgoing lepton momentum and direction. So we measure the angle and energy of this muon, and then we map that to how many neutrons are produced. And hopefully we'll also break that into more exclusive final states as well. Understanding neutron yields from neutrino interactions is critical to understanding and controlling critical systematics on long baseline experiments such as NOVA and DUNE. In addition, neutron tagging is very useful in a number of astronomical and rare process detection efforts. The presence, multiplicity, and absence of neutrons is a strong handle for signal background separation. For example, in proton decay, the presence of neutrons is indicative of atmospheric neutrino backgrounds, whereas the proton decays themselves are very unlikely to produce any neutrons. And similarly, when looking for diffuse supernova neutrino backgrounds, the presence of any additional neutrons beyond the single neutron you would expect from inverse beta decay, that could be used to tag and remove higher energy backgrounds. But if you're going to go through this exercise of removing the backgrounds and you want to estimate your signal purity, you need to have a very accurate understanding of what is the neutron multiplicity that you would expect from the specific class of background events that fake those rare signals. Before I go any further, I want to kind of walk you guys through just a little bit of the mechanics of an A.N.N.I.E measurement. So we have a prompt neutrino interaction that occurs in coincidence with the beam that produces a high energy muon, and we want to measure the direction and energy of that muon. Sometime later, any neutrons that are produced by that interaction will thermalize in the water, where they're captured by gadolinium, producing flashes of light that we can count. It's very important when doing this measurement that we have good vertex reconstruction for 2 reasons. For one, the length of the muon is our measure of the muon's energy, and that we need to get the starting point right. And for the other, we want to select a sample of events that's far enough from the walls of the detector that we get good neutron containment. Now, before we could endeavor to make the physics measurement we want to make, we needed to really understand any neutron backgrounds, beam-induced neutron backgrounds that we would see in the Hall. In particular, we built an implementation of our detector, partially instrumented implementation, and ran it over 2016 and 2017 to characterize any background neutrons we would see in the A.N.N.I.E measurement. These backgrounds were found to be small and were mitigated by the layer of water that we've designed to be above the active region of our detector. They come predominantly from what's called sky shine. At the beam target, a lot of neutrons are produced, and they can actually scatter through the air and downscatter into our hull since we lack overburden. This work led to our first A.N.N.I.E PhD, and if you're interested, you can read Steve Gardner's thesis, and it will soon be our first publication as well. The next ingredient in making this measurement is the enabling technology. A.N.N.I.E leverages several new advances in neutrino detection technology, the first of which is the Large Area Picosecond Photodetector, or LAPPD. LAPPDs are 8-inch by 8-inch microchannel plate-based imaging photodetectors. So if a photon hits, you can actually tell where on the detector it hit. And they provide single photon time resolutions well below 100 picoseconds and millimeter scale spatial resolutions. These advanced new photosensors, I'm relieved to say now, are commercially available through INCOM Incorporated. And I'm also happy to say that the A.N.N.I.E collaboration has purchased and received all of our initial 5 LAPPDs for our physics measurement, and in fact, 2 of them arrived at Fermilab yesterday. This fall, A.N.N.I.E will become the first application of neutrinos in, the first application of LAPPDs in a neutrino experiment. As I mentioned, LAPPDs are important for vertex reconstruction, which we need in order to fiducialize our events, maximize our neutron containment, and also optimize our energy resolution. And our simulations show that just the addition of those 5 LAPPDs gives us a much better vertex resolution by a factor of 2 than we would with the PMTs alone. And we see a similar improvement in our directional resolution, which will help with multi-track event reconstruction, and this gives us a very good energy resolution of 5.8%, and that's inclusive over all of the muons. This is the muon energy resolution in our detector. Testing of LAPPDs is nearly complete, and preparations for summer deployment are underway. The LAPPDs have all performed with resolutions consistent with our requested specs, which is to say, again, better than 100 picosecond time resolution, gains of 10 to the 7, and the few millimeter spatial resolution. These are 2 plots from an upcoming paper showing for one of those LAPPDs the 64 picosecond transit time spread and a peak single photon amplitude of the signal of around 31 millivolts at 50 ohms, which is a very nice signal size for separating photons from background. The other enabling technology is gadolinium loading of water. Efficient neutron counting is made possible by gadolinium loading of water. Gadolinium has a very high neutron capture cross-section for thermal neutrons, and on the order of tens of microseconds, it captures these neutrons, producing this these delayed flashes of light from the 8 MeV gamma cascades, which produce detectable Cherenkov light in the detector. When we have gadolinium loaded our detector over the summer, this fall, A.N.N.I.E will become the first gadolinium-loaded detector on a beam. We've benefited a lot from prior work in developing gadolinium loading and compatibility of detectors, particularly from our collaborator Mark Vagans and his work on EGADS. But we've also contributed a lot of, I think, novelty to the discussion. In particular, we've developed a system that works well and is low cost for smaller deployments of GD water. In particular, we've done a lot of work on gadolinium compatibility with different materials than have been used in other detectors, and we've developed a method for making low-cost resins with commercially available materials. Just to put it all together, A.N.N.I.E Hall is located on the booster neutrino beamline right in front of the SB near detector. We're not the big building, we're the small building right there, but it opens up into a 3-story shaft. The A.N.N.I.E detector goes at the bottom. This is the former Saiboon Hall, and this is actually before we repainted the MRD. It's got the Saiboon markings. Our detector, the main target, is a gadolinium loaded water volume. It's 13 feet tall by 10 feet in diameter. Inside is a structure containing an array of conventional photomultiplier tubes. These provide the quantum efficiency for efficient neutron detection, and of course the LAPPDs, which give us our precision track reconstruction using timing. Upstream of the detector is our front veto, which vetoes any muons entering from the outside produced from neutrino interactions in the rock. And downstream is our muon range detector, newly refurbished and fully 100% recycled from Fermilab parts. That basically gives you a measure of the energy of the neutrinos based on how deep they penetrate. Our detector deployment, as I mentioned at the beginning, is going to begin in the next 2 weeks. Full commissioning and calibration will start this summer, and the detectors should be fully physics ready in time for beam taking in fall. I want to bring your attention to these slots here because these are how we deploy our LAPPDs. We can actually deploy them in situ to the fully filled detector so that they're both removable and so that we can add more, which brings me to the point that A.N.N.I.E is designed to be flexible and that new additions can expand our physics reach. With expanded LAPPD coverage, especially in the backwards region of the tank, we're hoping to be able to do much better topological track reconstruction and therefore measure more exclusive final states. And then something where there's a lot of interest both within and outside of the collaboration is the possibility in the future of adding water-based liquid scintillator. This would basically give you both Cherenkov and scintillation light, which with fast timing allows you to separate the prompt Cherenkov light that arrives early from the delayed scintillation light, giving you the track reconstruction and topology of Cherenkov, but the energy resolution and sensitivity to non-Cherenkov detectable particles such as proton recoils, and that again will expand your ability to do more detailed nuclear final states. Just to wrap up, A.N.N.I.E is a first opportunity to test many of the essential technological and experimental techniques relevant to next generation neutrino detectors. We're also performing highly efficient and detailed measurements of nuclear final states that are very relevant to long baseline programs like NOVA and DUNE, and also relevant to rare searches like DSNB neutrinos and proton decays. And we have a rich landscape of physics measurements to make and experimental techniques to develop. And I'd like to wrap it up on the point that there are many opportunities to expand the scope of the experiment and opportunities for new groups to have a major impact. With that, I'd like to thank Fermilab, without whose strong support and help and amazing engineers and technicians, we wouldn't be able to get this experiment to where it's gotten. And also thank you for listening. Oh, and to our DOE support. And thank you to everybody for listening to the talk. And I would like to open up to questions.
Great.